Nina, I'll let you take it from here.
Well, thank you, Janice. Much appreciated. Really happy to be here, be part of the presenter group for ISE. It's been a joy to be back involved. I've attended the conference numerous occasions, and of course, like everything else in the world we're in today, we seem to be doing everything virtual, or most things virtual, as we try to adjust to this new normal. With respect to trends in fiber optics, we're going to talk about trends in a couple of different ways. Janice gave us a good introduction as to the type of different topics that we talk about: FTTX, outside plant, fiber to the antenna. We do in harsher environments, enterprise networks, and so every application sort of has their new and unique methods of designing and, of course, installing the solutions. But what are the market drivers behind? What's causing a lot of the new technology that continues to evolve, and sometimes new revolutions that take place? Well, one of those drivers is the bandwidth needs. The continued need for growth in bandwidth, getting more data. And certainly today, we can see with all the Zoom activities, various webinar platforms, GoToMeeting, Adobe Connect, or whatever they might be, Teams, and so on and so forth. The list goes on, doesn't it? And we find that we're really drawing on this. And so one of the things that really helps us to appreciate that, well, we need to get broadband in every area. And certainly this is something that's one of the drivers behind it. We think about the higher network speeds that are needed, right, in more places, right, that farther the reach. On an e-commerce side, the mobile payments that we make, all of us generally today, or most of us, use this platform as well. We look at the coverage that's needed. Certainly we've had 4G coverage, but as we go long-term and continue to evolve, we can see that we're approaching, right, the 5G applications and wireless infrastructure. We look at fiber to the rural areas, even fiber to the farm, and a deeper penetration, of course, fiber to the desk, which is not new, but it's continuing to evolve, isn't it? And of course, we want the speed faster, so revenue is a big driver, right? Our service providers are in a highly competitive circumstance and situation. They want to be in a position to deliver a specific service to a specific customer. So we're just going to take a look here at what we're going to do is break this down as far as evolution and revolutions in the fiber trends. And fiber continues to evolve. It's, when it first got deployed in sort of the late 70s and early 80s, we probably never realized that approximately 4 decades later, we would be having this kind of circumstance and these kinds of bandwidth capabilities and reach even today. We just probably never realized it, but we can see it taking place. You think about even just little things that takes place now, and even virtually what we're doing with all our circumstances, not just in training, but how about telemedicine and other opportunities that we all have now to use remotely. And certainly this has been beneficial to all of us. Now we're going to look at various different topics in an evolutionary way, as we said, in a revolutionary way. So we know that fiber tolerance in the fiber itself is very important. Now, when fiber was first introduced, maybe the tolerances weren't quite as tight as they are today. But that's something that's been improved on, been evolving through the years, through the decades. So we have lower fiber loss today. As a result, when we're splicing fibers together, we have lower splice loss. And so a lot goes into that, the concentricity of the glass, the ovality, the roundness of the core, and the cladding of the glass. And the manufacturing processes have just improved so immensely and become even greater. Lower cost splicing equipment today that we can see as well. Different technologies that we use because of these improved tolerances, and we'll get into that. One of them happens to be ribbon splicing. When we get into ribbon splicing, because of these improved fiber tolerance today, we can see now that's been a benefit. And sort of higher split ratios as well. Well, what's the impact on the technician? Well, we have increased productivity, increase expectations in our productivity, and increase pressure on the test accuracy and the technique. So when it comes to uh, testing our fiber optic networks, not just on the splice side, on the network side, and even on the connectorization side. We understand that we have to meet minimum intermatability and interoperability for various standards depending on the application. It might be TIA 568 if it's inside plant or campus environments, and it might be Telcordia GR20 if it's outside plant or other outside plant standards, just as an example. Now, we're going to talk about a little bit about evolving technology that is somewhat recent but not brand new, and that's been evolving over the years with 200 micron fiber coating. And so that is somewhat evolution in the sense that we look at, we have a decades old standard where that we had two kind of typical outside diameters for our coating or buffer, if you will. And that was 900 micron, which would be tight buffer, and 250 micron, which would be loose tube or loose buffered, as some might call it. Some of that terminology just stays with us through the years, doesn't it? Well, what's the benefit of having a 200 micron coated fiber? Well, there's a lot of benefits in the sense that you have much more compact cable designs, much higher density cables in a 1-inch diameter, or even less of a footprint. And the installation efficiency becomes less time in some cases. So we're able to get a number of 200 micron fibers in the cable and get a better density in that particular way. So what's the impact on us, though? Those who might be a technician. Well, splicing and prep tools have to be looked at. Now, when you're stripping off 200 micron coating fiber as an installer, usually the tools are sized so that you can take 250 micron off or 200 to get to the outside diameter of the glass or the cladding, which is 125 microns. So that hasn't changed. It's the coating diameter that's changed. We've gotten it to reduce it from 250 now to 200 micron. Does this mean that all our applications that typically use 250 micron coating are going to be obsoleted? Not at all. Certainly for many years to come, that's going to be a typical diameter that we see in traditional loose tube outside plant applications. But maybe in certain high density applications where we need that extra space savings, we'll see some of the 200 micron coating being used. It's lighter weight. It could be very compatible with existing designs. And we'll learn a little bit as we go along about the splicing applications as well. So looking at the next slide, as we can see, an excellent depiction of the coating. What was 250 micron is now an outside diameter of 125 micron. And you'll notice that in this image, the outside diameter of the cladding or the glass is still 125 micron. It's just the coating size itself is smaller diameter. So what's the advantage? Well, good depiction in the upper left image, where in some designs you have 24 fibers that can fit into a 12 fiber tube. So you doubled your density. And that's a huge advantage in many applications, especially when you need the density as well and the space consideration. But the glass, again, the outside diameter of the cladding stays at 125 microns. So regardless of 250 micron or 200 micron, we can see the outside diameter, the diameter of the glass will stay the same. This reduces the weight of the cable. Now you might wonder, well, is this as rugged? Is it as robust as 250 micron? Well, if you think about it, the 200 micron has to still meet tensile rating like 250. It has to give you the same mechanical protection like 250 micron would. And it acts as a moisture barrier sometimes, and also it gives you a mechanical protection. So all these features still have to be standard compliant with 200 micron cable versus 250 micron. So we can still have the confidence in using this particular design as it emerges more and more in the industry. So when we look at the next slide, you'll see a good example of how it's fully compliant to the fiber standards, just like 250 micron would be, right? It would still need to have the same proof test, the same tensile rating as we mentioned, but look at the density that you're able to achieve. And again, it's compatible with most of your existing hardware. But now here's where a little more research comes into play, because you have to give consideration when you're splicing 200 micron fibers to 250. Now, when you're dealing with single strands of fiber, that generally is not too big a concern. We have good splicer technologies today that can align quite accurately. But there might be some issues or concerns when we're splicing 200 micron to 250 micron ribbons. That might be something we have to give consideration to, and we'll discuss that a little bit further as we develop this point in this theme. But we can see 200 micron has certainly emerged, and it's not necessarily taking over every application. It certainly isn't. But one of the things we can confidently say is that as the need for fiber in general increases, not only is 250 micron going to emerge more and more in many applications, but because of that, in certain applications, 200 micron will become even more prevalent as well. Now, this is a good example of some of the splicing considerations that we have to think about. And sometimes we have to even think about it as designers, planners up front, to making sure that when that handoff does take place, eventually it goes into the installation world, and they have to be up to speed with the technology, with the type of equipment they need and the particular manufactured equipment they're going to use. And the manufacturers become very adept at getting the equipment and the tooling to help with this emerging change. So we want to be aware when we're fusion splicing 250 to 200, it should be compatible, of course, with the existing equipment. 250 micron, though, ribbon to 200, what are we going to do? We might run into some concerns here because of why? Well, it's depicted for us in this image because of the pitch differences. And if you look at the diameter of the pitch differences between 250 micron and 200 micron, now we have to give consideration to that in our splicing operation. When we look at that, we still see the same color code, right, in both the 250 micron as well as the 200, blue through aqua, for the 12 strands of fiber that's being depicted here. What we need to do, and maybe the biggest takeaway in this particular slide, is contact our splicer manufacturer for information on how to handle this pitch difference. And they can be very helpful to us in that regard in helping us do that. But that's something we want to plan for up front, especially if we're designing or looking to design or plan for a 200 micron deployment. We would want to contact the manufacturers up front to be able to help us with that, that kind of tooling in application. And so we can see, though, it still can be done. And we think about it, even not just splicing, we think about connectorization. Whether it's 200 micron or 250, it's the cladding, obviously, that gets bonded to that ferrule of the connector, and that cladding size is still 125 micron. So we can see a lot of interoperability, intermatability still being able to exist, even though we're going from 250 to 200. Good depiction here in this particular slide. We have existing cable designs with 200 micron fiber, the little UM there with the little hash mark, that's micron. That signifies micron. So look at the differences when you go all the way down from versus a conventional 144 fiber to 200 micron. Look at the diameter difference there. And we can see that 12 tube versus a 24 tube, a huge diameter difference. And that's really what the benefit exists there. It's a nice depiction of the density and the space savings that we achieve. Now, besides the 200 micron fiber that we've talked about, maybe what's become a little bit more revolutionary recently is the ultra-high density cables, if you will, or collapsible ribbon cables. Our manufacturers will have their different manufacturing name to the collapsible ribbons, but this really goes a little bit beyond the evolution side of things because it helps with new technology significantly. Benefits, what are they? Well, you have new ultra-high density cable architectures, smaller diameters, smaller lengths, on the reels, fewer splices, less waste, smaller closures, as it mentions there. Now you have more complex network designs and splicing plans, so that comes into play with your documentation and with tracking, of course, your splices And when we get into examples of mid-span or ring cuts and those kinds of things, that comes into play very significantly. And the installation itself can be faster. And the concept of this is that these ultra-high collapsible ribbons, they sort of collapse on each other or roll into each other, if you will, as opposed to the traditional flat ribbons that are stackable. You have the blue through ochre that are laminated together. They're sort of glued together, really, with a bonding agent, and then they stack. Well, now these collapsible ribbons are a little bit slightly different when they roll into each other, if you will, or collapse, and giving you the ability of having higher density as well. While the impact, of course, on those installing this or the technician is that maybe new tools might be needed for preparation and the splicing, but you might be surprised that the splicing of collapsible ribbon fiber versus your traditional flat ribbon is not altogether that different. It's a similar process, but the tooling might be slightly different. And just understanding the bond points on the collapsible ribbon, there's staggered bond points in whether it be number of strands, one strand or two strand. Each manufacturer does it a little differently, and it significantly helps us in the field to get the high density that we're trying to achieve. You might have new splice closure parameters, new different sizes. Restoration is more of a critical approach, more skill needed just in terms of handling the ribbons. And you have to really take care to identify your specific fibers. But in that sense, we should be doing that too in our current traditional flat ribbon networks as well. So this has been maybe a little bit more revolutionary, if you will, than the traditional flat ribbon splice that we see. Now, good example here of a couple of manufacturers, collapsible ribbons. Now, if you look at the top one, that's OFS rollable ribbon, they call it, and you can see that the bond points that exist, they're staggered in some of the strands of fiber, and if you let that go, it'll roll onto itself as opposed to being a flat ribbon. Below is the AFL version, spiderweb ribbon. They name it that. It almost looks like a spider web as it opens up, right? So when you look at both examples here, OFS and AFL's version of it, they all fall under the umbrella of a collapsible ribbon technology. So the industry calls it collapsible ribbon, and of course, the various manufacturers will use various terms for it. Corning has one too, and certainly OFS and AFL, and we can see the benefit of these used in the field. Well, what does it help us do? Well, you can flatten as a ribbon, you can separate as well. And you can do mass fusion splicing, or you can use it individually. Now, for mid-spans too, this is very important. Some people call a mid-span a ring cut or an express technology, however you want to term it. But what we're talking about is mid-span when you bring in maybe an add drop location to that location along the cable run itself. Cable subgroups can be wrapped with colored strands in much higher fiber counts now than traditional ribbons. The new color coding, you have subgrouping that will be key for field staff to understand, the technician or the installer. And so if we ever design this kind of technology in our network, it would be good to make sure before we do the full handoff to the contract side, that this information has been communicated so that they can be up to speed with getting trained and educated on the different equipment that's used, and a little practice on routing the cables and so forth. Excellent example here of this collapsible ribbon design. We see ribbons in a traditional subgroup or new binders. As you can see, they're stacked, but now the rollable ribbon is a little different, where it sort of rolls onto itself, and they're organized differently than your traditional stacked ribbons. And look at the collapsible ribbon tube versus the conventional ribbon that has the stackable. Certainly a big difference. So you have much higher packing density here as well. And it can be organized very well too, as noted here in this particular slide. Now, let's look at a couple of these images here, staying on a theme of collapsible ribbon. You'll notice on the circular image below, look at the number of fibers looking sort of at the end of it, right? Together, how compact together they are from each other. There's no social distancing distancing going on with those fibers is there. They're just tightly compacted in together. When you look at the fiber counts, right, we know the traditional 144 fiber can go up to 3,456 fiber count. But now today, even some manufacturers are going double that, 6,912, in the same diameter, approximately 1 inch. Can you imagine that? So it's just amazing what's taking place. Maybe just over, you get the exact dimensions from the manufacturer, of course. You have armored versions that are available. Now, if it is armored, like any other cable, it has to be bonded to ground, meeting the code requirements. And of course, you have dielectric versions available, meaning there's no conductive elements to the cable whatsoever. You have water block dry core, very fast entry and cable prep, and you have good efficiency when you're dealing with mass fusion splicing. And you could also have some good cost savings in utilizing all these fibers that you have. Now you look at the image on the right, you can see the binder wraps that take place. So you have these subgroups and binder wraps now that we get used to in the collapsible ribbon fiber in the cable itself. No different than some of your other traditional outside plant cables. You can see it still has a rip cord, a pull cord to pull the jacket back. So there's a lot of similarity to it. It's just getting used to a little bit of the different technology in the subgrouping. And this is a good example of, many of us talk about this particular chart, and we look at it and we say it almost looks like the Morse code of color codes, doesn't it? But you look at the fiber count on the left side of your image, which says 144 fibers, going all the way up to 3,456 fibers. And the binder group started at 288, and then you can see the groupings, the binder units. Then you have ring markings. And if you look over to the far right, you can see that you have stripe ring fiber identification. So a number 1 would be 1 stripe. So you go blue, orange, green, and continue on through your color code sequencing. And so you can see it's based on what? It's based on the group binder, the spiral or the subgroup, if you will, the helical group binder of the subgroup, the stripe ring ribbon marking, and of course the fiber color within that ribbon, as well. Now we know a traditional outside plant loose tube cable, we generally might see, let's say we had a 48 count outside plant cable. Well, that would consist of your typical tube colors, blue, orange, green, brown, and each one of those would contain 12 fibers in it with the color code blue through aqua. So the strands of fiber have the blue through aqua color code, and of course the tube colors mirror the strands of fiber as well. So it's similar here. It's just getting used to the groupings a little bit, a little differently as well with the new color codes to consider. Let's move on to the next slide here. Now, this is also an interesting chart here as well when we look at the new color coding and marking methods example. And this is the dash marks that we're looking at a little bit on the right chart on the last slide, the far right. If you see the 1 stripe up top, all the way down to the 12, ribbon 12. And you can see what happens is you'll be blue, orange, green, brown, slate, right? And then you get your fiber in the group, and it goes on in that way, and it groups it so that the technician can adjust and understand what fiber they're dealing with, what color code they're dealing with. So it's just a different method, new color coding marking methods that they just get used to a little bit. It's not so difficult that it's going to be impossible. It's just getting adjusted to that and being aware of that up front. So this 200 micron that we talked about versus 250 has had a lot of benefits. The smaller diameter of the cable helps us, and you might say, well, how does it really help in terms of space savings? Well, here's one example of that. It's a good example here of a large reel of fiber optic cable, and you can ship a lot more length per truck compared to a conventional 432 count cable. That's interesting. And you have less waste, less loss. Well, the larger the diameter of the cable, if you have larger diameter coatings, larger diameter buffer tubes within the cable, means that I can only go so long in that cable as, the spools of fiber, you don't want them to be too much bigger than the truck that's carrying them, right? So as you go along now, I can get more length in that because of the smaller diameter of the cable as a result of the impact and the chain reaction that takes place with having 200 micron. And so that's a big increase. So the average length increases, across all counts, approximately about 35%. And you have much less waste, which is excellent over time when you're multiplying long distances and high density cables. And even for 100 meters, per 100 meters, look at the waste can be quite, less waste can be quite significant. This particular image is showing 15,000 foot reel with a 1728 fiber count here. So you can see that's a pretty large spool of carrying the cable. Now, with splicing operations, it's easier fiber separation, right? That's important when you're doing that, especially when we talk about a ring cut or a mid-span partial cable splices where we have small size and flexibility of the ribbons, right? We want them to be expressed into a small enclosure. When we say expressed, some fibers will be terminated locally there in the enclosure, and some will express in and out. So you might hear a term called mid-span express, ring cut, mid-span itself, that kind of thing. They're all synonymous, these various terms that we use. And you can see on the right side, the right image, and how these fit into the enclosure. This is a 576 fiber storage in the steel of access enclosure. And look at bend radius is really being maintained here. And you can see well done. And then you look at the image on the left, they're expressing all the way down there, peeling out all the way down to even a single strand of fiber. And so this is how you would manage it so that it's neatly done. And within the splice tray too, it can be neatly done and maintaining good routing, good practices for installation. And that's important to do as well. Now, for splicing, we have to think about certain considerations, right? Compatibility, productivity depend on what? Well, the task at hand, how detailed is it going to be, and the tools that are involved that we might need. Now, all manufacturers' collapsible ribbons are not exactly alike. You can't say one size necessarily fits all, even though they all might have the same diameter coating, or they might be very similar. One is rollable, one is maybe spider web or whatever different manufacturer might call theirs. Not every 12 fiber splicer will be able to splice every combination of encapsulated flat ribbon, like it mentions here, and collapsible ribbon. So you have to think about, well, what happens if I have one fiber with a 250 micron pitch that we showed earlier versus a 200 micron pitch? So the manufacturers are evolving with this tooling, and the key takeaway here, of course, is contact the splicer manufacturer for your exact requirements. It isn't that you certainly couldn't work through the process, but it isn't something that you would just say, well, consider it like flat ribbon, 250 micron, and we're going to splice this. We have to think about, the productivity and the task and what we're splicing. Is it ribbon splicing to flat ribbon, which can be done. And you think about these bond points and intermittent bond points, right? They're a little different than the flat ribbons because they're all glued together in this laminate bonding agent that acts like a glue together in the laminate. When you look at the staggered ribbons here, the collapsible ribbon, you have staggered bond points in various methods. Some manufacturers do one or two strands, some might do something a little different. And so, but all together, they have the idea we're going to roll this cable into itself, if you will, roll the strands of fiber into itself. So it's a little different than the flat ribbon. So there's a little more prep involved, nothing that can't be worked through. And as we emerge more and more with this, that pitch difference, particularly with the ribbon fibers, we're going to be able to work through that. The technology will become so prevalent that it would be like we were doing it right along, and it's not all that different, not all that evolutionary or revolutionary. Now, what are the benefits we have here? Well, let's think about the benefits and contrast that with a few disadvantages, right? Very few. Obviously, interest is going to increase in the demand for the data when we look at 5G deployment and the need for the strands of fiber within the fiber cable market, right? It's a pretty mature market. Like I said, late 70s and the early 80s, single mode fiber came into play, and there's been some progress with that. Like we said, the tolerance process has increased significantly, but there still remains a lot of room for more innovation, and we're seeing that. But some of the aspects of the collapsible ribbon designs can impact other tools and processes, and so those will continually adapt and adjust accordingly. So will we need new interductor closures for the inventory? Maybe not. We might not need. We might be able to use the existing infrastructure, but this is all part of the due diligence that's done, maybe in site surveys or planning up front. In construction managers, are we developing new processes, right, to take advantage of these benefits? And then when we look at the outside plant managers and splicing contractors, is our current tooling compatible with the company's specific cable designs? So our field techs trained to manage these high fiber count cables. The subgroupings that would take place, the routing of the strands, the prepping of the splice itself. As we know, the splice itself, anybody who's been involved with fiber optic splicing, fusion splicing in particular, the splicer does a lot of the work for you, but it's the preparation piece, even in standard ribbon or standard single strand splicing, that is most important, isn't it? Making sure you have the area that's suitable and clean for routing, the right heat shrink size, and so all these things would come into play here when we're dealing with some of the new collapsible ribbon technology. So there's a lot of benefits, and it's just maybe getting accustomed, and I wouldn't call it a real disadvantage, but it's something that we just got to get accustomed to the tooling required for this. And again, this is nothing too complex that we shouldn't be able to handle. Now, let's think about microducts and microcables. Microducts have been around a little bit, but they continually to evolve. The nice thing about the microducts, takes a lot less space. Micro, meaning, I'm not really trenching too deeply, am I? I'm not doing a big wide trench going all the way down. When I have all these issues I have to think about, OSHA requirements, maybe be even more for consideration. Not to say that they're not with micro trenching, but there's just a lot more parts and pieces to traditional trenching and traditional boring and horizontal drilling, that kind of thing, and plowing for that matter. So it could be a little bit faster installation. Smaller, lighter cables apply here, and you could put more fibers in a less space. So it does have a place in the industry, certainly. And the impact on the technician is the jacket walls need to be good cable prep skill, have to have good cable prep skills, so you don't cut the fibers, which easily could be done because these walls, jacket walls, are not that thick in some of the microducts. So we have to think about that, and even in the individual ducts. So new installation tools and techniques, right, for blowing the fiber cable will always continually get better. But some of these microducts in the fiber, you'll push the fiber in, or you might blow the fiber in. And on occasion, they can be pulled in as well. But traditionally, you'd be surprised in smaller point-to-point applications without bends involved or sweeps or anything like that. You can go a little bit of a distance just by pushing the fiber through these microducts. But there's less duct needed for the same fiber count, certainly. We can see a lot of benefits with that. Now, the cable placement, here's a couple of good examples. If you look at the upper right-hand image of a microduct there, and you have, you can see the lighted cables obviously have less friction on you. Now think about though, this versus traditional outside plant cables. Your traditional outside plant cables are going to have a much greater pull tension strength, but they may be for longer distances and that kind of thing. But these microducts, we can see you can still go some distance with them, but you see the top image on the left, you see you have 7 little microducts within that little structure. And interesting on these, they're lined as well to help prevent undue friction. Some of them are ribbed a little bit. They're edged a little bit, so ribbed actually is a better term, and so that you have less friction on the cable pulling in, and these are excellent for utilization of duct space. perfect for utilization of duct space. So your micro cables can be blown into micro ducting systems, making these additions really, really easy and you know, quite commonplace to accomplish. Fewer setups. You have intermediate pulls that can allow for longer lengths, even in each day. Uh, and so smaller cables for equivalent fiber counts obviously will have to have more efficient duct usage, but fewer ducts overall and lower cost is the point. But now look at the image below. It's something interesting. These are your traditional kind of outside plant cables that you would see, and you'll see a piece of what is known as Maxell sort of interduct that's used there. You'll notice why it is used there. It's in one cell. One cable is going through one cell. The other cable is just shown how it can be pulled on the outside of that interduct. And that's made up of certain materials. Sometimes in the past, it's been known to be made up of like nylon or polyester, or the different materials that are used, could be used here. And this Maxell duct is very nice for helping to prevent pulling tension and friction on the cable. And so it makes it easier because you never want to pull cable over cable. And so this is a good example of how that would be used over here and prevent damage to the cable by having such interduct in place. So there's a place for all these different applications as well. Now, let's look at the next slide. Now we look at micro trenching. Excuse me. This is somewhat evolutionary. You know, your traditional trenching takes a lot of space, doesn't it? It's not easy to exactly just come in and just disrupt the whole road and disrupt the whole maybe a neighborhood and sidewalk without going through a lot of planning and approval steps up front. Well, as you see here, you can have less permitting. Doesn't mean you're going to completely remove the need for permitting in all cases, but it means that it'll be less that's needed because less disruption in the area. Like it says here, you wouldn't have to shut down the roadways. Less disruption at the customer locations as well, which is a huge benefit. And the impact, of course, on the technician is that many new markets open up for us to be able to install. Might be that new cable or new equipment rather is needed. And then we have to have different materials that would cover the trench than your typical wide trench here when we deal with micro trenching. Excuse me, a little tickle in my throat.
Mark, go ahead. Stop for a second. Take a drink of water. I feel bad.
Well, you know, I'm from Boston. I'm from Boston. I'm from Boston, so we just got to talk and talk fast. You know, that's how it goes.
I know. No, just take a drink and.
Excuse me.
Feel,
So I hate that when I'm talking halfway, half hour. I tend to get a tickle in my throat, and it just you have to stop. But thanks for your patience.
No worries.
Micro trenching. Now, micro trenching characteristics. What is it? Look at this. What we have to consider here. As you can see, there's less space that we're disrupting. And it's maybe a 1 to 2 inch wide trench, no more than 2 feet deep. And this happens to be, looks like a concrete surface here that exists. And interesting here, we have less disruption, no real backfill. Can you imagine the OSHA requirements in some of the larger trenches that you're involved in? And the backfill has to be so far away from the edge because it can collapse in. We had a kind of a tragedy in the Boston area a couple of years ago where a couple of individuals died in this traditional trench because of the backfill and the instability of the earth, and it was kind of tragic. The trench was too deep. Well, here you have a micro trench, 1 to 2 inches wide, and now, like it says, maybe 2 feet deep. This is not to say that you wouldn't need to get permitting. You certainly would. But the area that you're looking for the permit is so much greater. Now, think about typical trenching. So much less, I should say. Think about typical trenching. Not only am I getting a permit for the area that I'm disturbing, which could be 3 feet wide or whatever it might be, or the width of the bucket truck and that kind of thing, but I have to get the permit approved for the complete area that I'm disturbing, which takes on much greater significance. So micro trenching helps to avoid maybe that depth of permitting that you would need in the traditional trench application. So you bring your microducts in, but now you notice you might have a vacuum system with that. It looks like a machine up front there, and they have these saws that cut through the concrete different depths, different sizes, and so forth. And if you look at, they go down deeper into that trench and get you the depth that you need. But you still have to make sure you do what? Anybody in outside plant, in engineering and installation will tell you, and design will tell you that you need to get approvals and locates. That's really a requirement, is to get you locates so there's no other services that you're disrupting. I happen to have a neighbor not too far from me that had kind of a property dispute, I guess, down the road from, I don't really know them, but down the road from me. And so he was able to prove that it was his property. But, you know, before he could dig anything, this person was trying to sell a property that had the driveway on the other neighbor's property, and the other neighbor took offense to that. I didn't like that too much. And so it wasn't disclosed, I guess, to the new buyers. And so he was trying to figure out how to handle it. Well, he got a survey done, proved that that driveway that the other neighbor was using was on his property. And then what he did is he went ahead and got the location done, right? And when he got all the survey done. So he had where the gas was located, the yellow markers, and blue for potable drinking water, red for power, orange for communications, and so on and so forth. So he had all this done and locate where the facilities were. If he had dug into that driveway, even though it was on his property, if he had dug into that driveway, even though it was on his property, and hit another service, he'd be liable. So he did all the right steps, and you do need to get permitting for that. Well, this becomes so much easier. Long story short, in the other end, he ended up digging out the driveway on himself one Saturday morning. I was watching from the window way down the street and said, wow, looks like Paul Bunyan out there with the axe and pick, and he was able to get it all done. I don't know how it all worked out with the two parties, but hopefully it was peaceful. But interestingly, he did all the right steps. A little dramatic the way he did it, but yes, all the right steps were done. Well, now microtrenching helps to avoid a lot of that because it doesn't mean you can't hit anything, but the likelihood of disrupting other services becomes less. And 2 feet deep in the Northeast is not all that deep. With some of the services that we deal with even deeper, we get below the frost line. And now when you cover that opening, you backfill generally might some kind of elastomer, like it mentions, a grout. Sometimes some put asphalt over that, or some other means of doing it, or hard top and that kind of thing, so that you can drive over it. You could really almost drive over it there now the way it is, but it's certainly not you wouldn't leave it undone like that. But again, get the locates, get the permitting. You still need to do all those steps. It's much less intrusive, and it takes up much less time and effort that the traditional trenching would provide. So this small size, of course, limits the size and the number of cables. Now, what we're going to see as time goes on is more increasingly complex architecture. So we have a dual check mark here, one for evolutionary, one for revolutionary. And you'll see a term called point-to-point and point-to-multi-point, right? So we can see these architectures. We've heard these for a bit. They've been there. Point-to-point, you might think of it as a sort of an Ethernet network. You have a fiber in between the electronics. And then point-to-multi-point might be something like a PON network, passive optical network, or GPON. Gigabit PON optical network. Well, the benefits here, as it's talking about, is you have multiple services on the same network, and we're seeing more of that. So while it's evolutionary, a lot of this is more evolutionary. You think about cell sites and the 5G deployment taking place, and then you might be running fiber to the business at 10 gig or even greater network speed. Well, you can use a lot of the same wavelength spectrum and multiplex and combine more than one service. So there's a lot of benefits to this. We talk about 5G and the Internet of Things supports, right? And we also can think about the software increases needs for these applications as well. Now, the impact on the technician is you have more mid-span entries, right? So that means you have to be a little bit more precise in how we handle this. And documentation comes into play here, because as you do an express entry or mid-span along the span of the fiber run, and you maybe add a drop location, all these things have become more critical. documentation is extremely critical. One of the challenges we have in our industry, and like other industries, is good current documentation. And I think we've been getting better with that. But even in our existing infrastructure, what's important is that what's really important is that we continue to update our drawings, some known as built, right? And that kind of, that becomes even more important to do when we're getting with these increasing the complexity of our architectures. So we need to think about that as well. Become wavelength aware, new wavelength aware in our test equipment as well, as it mentions. And interesting here, again, this is a little bit of evolutionary term because we have an expanded use of the spectrum. Well, the spectrum we're talking about here is the different wavelengths that we can use, and we can combine that with our multiplexing. So if we look at CWDM, which stands for coarse wave division multiplexing, and DWDM spectrum use, and this is going to be very important in the growth in the various markets, future fiber markets that we have. So this is enabling the technology that can take advantage of the full spectrum. You know, years past, we wouldn't be able to do that, but over the recent last few years, because of the low water peak fiber that we use, if anybody's familiar with the ITU standard that talks about low water peak, ITU G.652D is the suffix to that. Well, that's low water peak in the sense that it allows you to use the full spectrum. And now you have 18 different channels that you can use over these wavelength spectrums, and they're 20 nanometer spacing apart. Well, that gives a lot more flexibility, doesn't it? And of course, DWDM is even denser than that, and we can see the impact that it has on that. So the spectral response of the fibers becomes important. Now, one of the things you have to think about as the impact on the technician is a lot of times you're adding on or connecting new fiber plant to an existing fiber plant. And that fiber plant could be, that you're connecting to could be of a legacy ilk, if you will. And maybe it isn't up to speed in terms of when that whole system is connected together in terms of fiber characterization that needs to take place. You deal with dispersion, chromatic dispersion for single mode fiber, and another type of dispersion, which is random, is called a PMD, or polarization mode dispersion. Particularly if you start getting into higher network speeds, these become an issue. And that's more random, has to do with maybe older legacy fibers. If you're building new fiber plant and it's just installed new plant, most of your modern fibers today don't have those kinds of complexities, the same situation that you have with the older legacy fiber plant. So that's something to give consideration to. So that might be something that could be a concern for us in the field when we're trying to characterize and requalify our fiber network. So we can see the benefit of using this expanded spectrum. And I think, Janice, that's going to take us over to you. We have a few minutes left maybe to answer a couple of questions, hopefully. And I think that whatever questions we're not able to get to, I'm sure we can work through that with Carol and Andy and get those answered for some of the folks attending your conference.
Yeah,
but thank you
absolutely.
all for joining.
No, thank you. This has been fantastic. And I know we technically end at 2 o'clock, but if those of you who need to go, you can check back into the recording, and we'll just hold the Q&A and go through them, finish them all, so you can listen to them on a recording version if you can't stay on the line with us. So we understand time is precious in these days. So thank you again, Mark. We're going to begin kind of backwards here. We'll start at the bottom and go up. So we'll start with, will the standard become 200 micron and get away from 250 micron standard loose tube fiber?
That's a good question. You know, doesn't really appear that we're going to have a complete eclipsing of 250 micron fiber. The standard loose tube cable and your traditional outside plant applications look like they're going to be staying in place for quite a number of years, certainly in my lifetime, and maybe many others too as well. And when it comes to the 200 micron, just as fiber deployment expands in many areas, 200 micron will expand along with it, but so will 250, and we'll still be using the traditional 250. And keep in mind that 200 micron that expands, it will be standard compliant, just like the 250 micron.
Okay, thank you. Then this is a little bit relatable. Will stripping the jacket off the 200, is it or is it just Forgive me.
Yeah, the little with the hash mark stands for microns. Yeah.
Microns. Listen to me. I'm like, Yeah, sounding like a fool. Sorry, guys. I'm not the fiber specialist. No. I'm the big picture person. So, all right, this is a question about stripping the jacket off the 200 micron be more difficult than the 250 micron.
And so, again, and just so I understand the question that was asked there, will it become the standard? Is that what you were asking?
No, this is asking about the stripping of the jacket off the 200. Will it become more difficult than the 250 is what they're asking.
Oh, okay. Thank you for that. Not really. I think most of the tools are compatible to take off the 200 micron just as well as the 250. If you think about it, when you're stripping off that coating of a buffer, if you will, you're getting down to the outside diameter of the glass or cladding, which is 125 micron. And whether you take 250 off or 200, the tool manufacturers have come up with the ability to be able to take that, strip that amount off to get to the 125 micron glass. So generally, I think the tools will be compatible with 250 or 200. There may be some exceptions in certain areas that you might have to make an adjustment.
All right, thank you. Here is a question from somebody at Windstream asking, with efforts to increase concentration of fiber count in the same size tube, do you anticipate $1 per square foot going up and OSP tightening up on their design lengths and order lengths to minimize waste on the reel?
Well, the second part of that question is, yes, I do anticipate minimizing the waste as you were asking. On the per square foot, it's an interesting question. Well, revenue certainly drives a lot of what we're doing, right? And so that could certainly happen. I wouldn't be in the best position to give you details on that, but it would not surprise me to see that.
Yeah, I agree. Any comments on Corning's rocket ribbon versus rollable ribbon?
Yeah, that's just, and Corning has their name of rocket ribbon cable. I thought maybe I didn't mention Corning rocket. I think I said Corning, but I forgot maybe to mention rocket ribbon. They're just a different style. They're just it's a different Corning's manufacturer. It's no different than the requirements of AFL and rollable ribbon by OFS. They have to be compliant, standard compliant, and they have to meet the performance criteria as well. I think it's just a matter of preferences with the installer and technician, what they become more familiar with.
Okay, what they're more comfortable with. All right, great, thank you. Could you point to benchmarks on productivity for fiber installation? Any splicing, terminations of legacy versus new compact fiber cables? Any benchmarks you refer to?
Yeah, I'm not quite clear on the benchmarks you're looking at, but maybe the benchmark is to the benefits of going to the newer fiber versus the legacy fiber. I think a lot of that's. Is that what you got out of that question?
I think so. Yeah, the productivity.
Okay, so I think what we'd be looking at there too is the network speeds are going to be a big driver to determine that.
Okay. Yeah, that sounds right. Let me see. If there's more that you want on that question,
we can give more detail to it.
Exactly. We can follow up on that. All right. Also, is there a bend radius with the high count rollable fiber cable still relative to the OD of the cable?
Well, again, the manufacturer will give you usually what the bend radius applies to. It's certainly significantly reduced compared to traditional fiber outside plant cables because they have a, you'll see two numbers sometimes that traditional cable default to under pull or under load. It's like 20 times the cable diameter, which is pretty significant. Even after it's installed, it's 10 times the cable diameter. Well, with bend insensitive, not necessarily needed, but I would have you refer to the spec sheet of the particular cable manufacturer you're getting the cable from.
Okay. Here is a question about what is involved in requalifying fiber for WDM deployment.
So when you think about for requalifying the fiber, you're getting into really making sure you're dealing with fiber characterization, making sure it can meet the modern network speeds today, not have pulse spreading and dispersion testing. You get into spectral width and spectral attenuation and polarization mode dispersion and chromatic dispersion, which means chroma, color of light. You have different lights traveling at different speeds. That all has to be looked at and maybe requalified to make sure it meets today's requirements.
Okay, great. Here's someone asking, do you see any reason why rollable fiber wouldn't be put into OPGW?
Yeah, it's an interesting question. I have personally not, anything we've done with OPGW, I've not really personally seen that used. To answer the question of what, could we see anything prohibiting that? Not necessarily. Maybe just though the cable diameter design with the cable itself, and that might be something I think Janice and Andy, we might just run by Cameron on that. Another one of our persons who deals directly with OPGW.
Oh, got it. Perfect. Okay, great.
Nice question, though. Nice question.
Yeah. And then they can go into detail with you on that one, Greg, just to let you know. Let me see here. Another one. Is there a limit to the length of the microduct, and do these ducts include a pull member or string?
Well, the ducts could include a pull member, a string. They traditionally don't, though. Usually you're pushing or blowing the fiber in. So you do have applications where you could use the pull string in those areas, but that's not as common. It's very not common. And lengths can go quite some distance, and it really depends if I got to make a sweep or that kind of thing. You see it a lot in metropolitan areas or campus environments. So your lengths are usually limited to the structures themselves.
Okay, very good, very good. I believe we have answered the questions right now, and as Mark mentioned, we'll get back in touch with those two individuals to kind of go into a little more detail. At least Mark and Andy and their team will. I will not, as we understand. I am not the expert in this at all.